All right, so we're going to do the review questions, the remainder of the review questions, practice problems, extra practice problems. Tomorrow is the exam. I'm going to ask you at the end of class if anybody plans on staying for tutoring, because frankly, if I don't have to stay, I don't want to stay either. But if you intend to be here, let me know that. All right? Okay. Ready to go?
Yes.
Okay, here we go. Pass. No, you don't have that option. And here we go. Describe the periodic trends of, now the question actually said, the previous periodic properties. So I kind of reworded this question if I remember correctly. I haven't looked at these slides for a few days. It is a Monday, yes?
We were wondering if we get our homework.
No. Oh! That's right. I'm sorry. So you don't have your homework that's my best practice. I got out of a meeting with the board just in time to come down here. So, yeah, I know. Thanks. What was that, ma'am? Did you say something? You have yours? Would you like me to put a grade on it?
You already graded mine.
Okay. It's already been in and returned. Okay. That's what you're one of those ahead overachievers. You're not like somebody that maybe hasn't turned it in yet. Okay. I apologize to those of you that I failed to make copies of your homework so you could review your own answers. I'm a terrible teacher. I should just quit now. No? Okay, we'll go on then. Oh, I'm going to make comments, so then you be quiet and I'll keep talking to you. Here we go. Describe the periodic trends of ionization energy. Increasing is...
What?
Or you say it however you want to say it. What's the trend?
Ionization energy is up and to the right.
So it increases up and to the right.
Same thing for electronegativity.
Electronegativity. What's the difference between those two, by the way? No. Don't look so much at your paper. Let's just talk to me for a minute. Do you remember what the differences between these two are? Let's just review for everyone. And I know it's not technically part of the question you volunteered to do, so I'm sorry, but ionization energy and electronegativity. What is the difference between the two? Or more, just basically, I've asked you to think about it from two different perspectives, right? One of these, I've asked you to look at it from the perspective of the atom that is trying to hold on to an electron, and the other one from the perspective of the atom who's trying to take away an electron. Do you remember which is which?
The away from an atom for electron is ionization.
Okay.
Is that wrong?
It's wrong, yeah. Ionization energy, remember, is the perspective of the atom who's trying to hold on to. Now, we usually put it in terms of how much energy would be required to take it away, but that's just minusculely more than the energy to keep it, okay? So for ionization energy, I want you to think in terms of an atom is trying to hold on. How much force is an atom going to use to hold on to the electrons that it has? And so anybody else that comes along with a greater electronegativity is the force to take away somebody else's. And if the electronegativity of one atom is just slightly greater than the ionization energy of the other atom to hold on to it, the electron's going to go. And if the ionization energy is stronger than the electronegativity, then it's going to stay. So that's the way to think about it. So the trend for ionization energy increasing, remember, you can say up and to the right, but what does that mean? It's increasing up and to the right. Electronegativity?
Increasing.
The same, increasing up and to the right. And atomic radius?
Decreasing down. Oh wait, is it increasing?
I don't know, you're answering the question. I'll critique
Down
you when
and
you're
to the
done.
left.
Down and to the left is what?
What? I don't know.
No, you're doing fine, Molly. Go ahead. Down and to the left is increasing. The arrows I've given you are all increasing trends. Ionization energy increases up and to the right. Electronegativity increases up and to the right. Atomic radius increases down and to the left. We could say it the other way. Ionization energy decreases down and to the left. Electronegativity decreases down and to the left. Atomic radius decreases up and to the right. See that? But the arrows that I've taught you here, up and to the right, down and to the left, are the directions of increase. That's the periodic trend. Pass it on. Okay, number 12. What is the fundamental difference between ionic and covalent compounds? At its most basic conceptual level.
Covalent is held together by sharing. Ionic is giving away.
Giving and taking, right. Good. So the fundamental difference, ionic compounds form because of the opposite electromagnetic forces that pull them together. And that happens because in ionic compounds, the ions are created by giving and receiving of electrons. They transfer the electrons. A metal transfers electrons away to a nonmetal which has a greater electronegativity than its ionization energy, right? So electrons are moving away from metals, making them positive, and to nonmetals, which make them negative, and then the opposite forces attract those two ions that are oppositely charged. For covalent molecules, it's covalent bonding. Remember, a bond is a shared pair of electrons. So nobody loses, everybody gains in covalent, because everybody gains a share of electron. Ionic, they give and take. All right, passing, here we go. Hey, don't infect the disinfectant wipes.
Oh, got me, Stefan.
13, what's wrong with the following formula? Mg2O2. Why is it wrong? Too bad you don't have a copy of that answer key, huh?
Is it because? Oh no, I have.
Guess.
Is it because Mg2O2 should like be Mg and O?
Should be Mg and O.
Oh,
Right. Why? First of all, we have to, that rule applies to ionic compounds. So we need to make sure this is an ionic compound. So we look at it, we have a metal and a nonmetal. It's going to form an ionic compound. Remember, ionic compounds, you got to look at the subscripts and take the greatest common factor and divide them out. So here 2 and 2 reduce to 1 and 1. So it should be MgO. Now, if it were a covalent molecule, this might, again, it wouldn't be Mg and O, but it would be a different molecule. It could very well be like C2H2. That could be correct, but it would have to be a covalent molecule. Okay? But ionics only combine in one way, and it's going to be the simplest combination, to have a neutral charge. So it should be MgO. All right? Go ahead and pass it on. And 14. What gases are involved in the Earth's three-tiered protection system against high-energy light that comes from the sun? Do you remember that lecture where we talked about the three different molecules? And we've got the gamma rays, the Hulk rays, right? And then we have the X-rays, and then we have the ultraviolet rays. Each one of those we associate with one particular molecule in the atmosphere, and how the system we have basically destroys that energy, dissipates that energy. So, do you remember that? Okay. I'm not going to draw it up on the board, but we had, first of all, the nitrogen molecule, right? Nitrogen, when two nitrogens form an N2 molecule, it's a homonuclear diatomic, so it's going to be an N2 molecule. Do you remember what the bonding between them is? This is for anybody. We'll just open it up, okay? The nitrogen molecule. Yes, sir?
Triple bond?
Triple bond, right. So nitrogen, it has 5 electrons. So when you draw the Lewis structure of that, it's going to have a pair plus 3 singles. When you put 2 of them next to each other and you bring all the singles together, it forms a triple bond. Both atoms C8. It's a neutral molecule because no electrons have been added or taken away. So it's a triple bond. That triple bond, the only, of those 3 different types of light, the one that can break that is the gamma ray. The gamma ray can break up the nitrogen. When a gamma ray hits that triple bond, the 2 nitrogens become atoms of nitrogen again, but the energy ray is completely dissipated. It's gone. So the energy breaks the triple bond. Now we've got 2 atoms of nitrogen which are close to each other, and what do? They immediately reform the triple bond, and now you've got another nitrogen molecule. So what's happened is, break it apart, comes back together. Break it apart, comes back together. The only thing that happens is the gamma rays that would come down and fry you, or Hulk you, get dissipated and they never reach you. Because the nitrogen is, the triple bond is absorbing that energy in the process of breaking up. The second type of energy we talked about was X-rays. X-rays aren't powerful enough to break up a triple bond, but they can break a double bond. And so when they hit a double bonded oxygen, an O2 molecule, oxygen has 6 valence electrons, 2 pairs, 2 singles. It's a homonuclear diatomic, so when the 2 oxygens come near each other, they form an O2 molecule with a double bond. Now, yes, the gamma ray could break it up, but the X-ray breaks it up. When the X-ray breaks it up, it completely dissipates the energy. It's gone. The ray is no longer there. And then we have 2 atoms of oxygen, which come back together and reform an O2 molecule. So gammas break the nitrogen triple bond. X-rays break the double bonded oxygen. And the third type of gas we talked about was, does anybody remember? Ozone. Okay? Ozone is an O3 molecule, which is kind of weird. Okay? But it has a double bonded, it has a central oxygen with a double bonded oxygen and a single bonded oxygen. And that single bond, when an ultraviolet ray hits that single bond, it has enough energy to break the single bond up. Problem is, when the single bond oxygen gets broken off of the double bonded oxygen, what happens? It becomes a double bonded oxygen and a single oxygen atom, which will probably be near another single oxygen atom, which will automatically form an O2 molecule, not an ozone molecule. Okay? It'll form O2. So of the 3 different gases, only one of them is not self-replenishing, the ozone. And that's why we talk about ozone hole. Talk about, worried about the effect of gases that are depleting the ozone, which will cause everybody to get fried, get sunburned. That's because that single bonded oxygen in the ozone is no longer there to absorb the ultraviolet rays, which means they come all the way down to you and you get a sunburn through ultraviolet radiation. So those three gases, nitrogen, triple bond, oxygen, double bond, ozone, a double and a single bonded oxygen. The homonuclear diatomics. And H. Okay, so you put hydrogen at the end as opposed to beginning. Most people start with the periodic table with H, NO, and then column 7. All right? HNO, column 7. And they're written with the subscript 2s. They all are possible as a single atom of hydrogen, single atom of nitrogen, single atom of oxygen. However, and so on. But whenever 2 atoms are near each other, they're going to automatically form a molecule between them with different kinds of bonds, but they're automatically going to form a homonuclear diatomic. Same nucleus, 2 atoms, 1 molecule. All right. Draw the Lewis structure for CH4. Just so you don't have to walk up here or be on camera, I'll go ahead and do it. Okay? So, CH4 molecule, what is it going to look like?
Well, I think the C will be in the center.
Center C, okay. So you have a center carbon.
Its dot's not like 1 all the way around.
Okay, so we have, well, 1 all the way around would be a big dot, right? But I think you meant a dot at each of the cardinal positions, right? Like that? Okay. Right. So there will be a hydrogen. Hydrogen has 1 electron. And then we're going to share them. So symmetry, 90 degrees. And then count up, okay, how many does each hydrogen see? 2, right? Is its octet satisfied? It is, because hydrogen is one of those exceptions. It's only looking to have 2. Carbon, how many valence electrons does it see? 8, good. How many is it looking for? 8. So the octets are satisfied for all the elements, and that is the molecule. So I'm going to skip past this because that's a wrong picture. That's the C2H4. Who's next?
So the P goes in the middle.
Okay, so we'll have a central phosphorus. Not potassium, right? Because potassium is K.
The dots are, there's 2 on the right, 1 on the left, and 1 above and below.
Okay, so it has 5 valence electrons. We have a pair we're going to show on the right, and then singles. All right.
And then the chlorines are on the right, left, and below.
Well, with this system here, we've got it. We're going to go ahead and put them all with the unpaired electron. Right, and then we're going to bond them here, here, and here. Is that it?
Do you need to put the other dots for the chlorines?
We do. Okay. This would be something that for shorthand I may skip, and I didn't want to do all of the PowerPoints and confuse you, but yes, all these octets would be full. So technically, that is the full Lewis structure for phosphorus trichloride, right? But hopefully you would see that if I did this, what I'm doing is I'm implying that the valences are all full. Okay, so it's not, I would leave it probably like that.
I thought it was a trick question you asked it was done.
Oh no, that's just the way I would draw it for myself, but for you all, add more dots. And frankly, for you all too, if the 2 singles were up here or here, they could be any way, but just for standard, while you're learning it, starting at 3 o'clock, going around and continuing and doing it that way, better just to have a standard. But if you saw this on a piece of paper and it was drawn with the unbonded pair up here and a chlorine over here with a single bond, it would still be right. So if you can take this and rotate it any way, it's still correct. Okay. FNO. Let's go. Yeah.
So it would be all 3 of them in a line in O.
Okay. So nitrogen's going to be in the center?
Yeah.
Why? Well, let's get a real reason other than it looks better that way. No, just go ahead and try. Why would any particular atom be the center atom?
It just helps the other ones feel there.
Yeah, so how do we determine which one, though, is going to be the center one, the pivot atom? Ma'am? It has the most unpaired electrons, yeah. So it's not, and sometimes I say that too, unbonded pair, but technically it's the most unpaired electrons. So like for chlorine, it has 3 sets of paired electrons and 1 unpaired electron. Nitrogen here is a column 5 element, so it has 3 unpaired electrons. Oxygen is a column 6 element, has 2 unpaired electrons. And what about fluoride? It's column 7, right? It has 1 unpaired electron. So nitrogen gets to be in the center because it has the most unpaired electrons. All right, so we're going to start with nitrogen in the middle. Going to go ahead, since nitrogen is in the middle, kind of assume that the other ones are going to be on the outside. And it could be the other way around. It's fine. But we'll just set it up this way. Now, how many Lewis dots are we going to put around each one of these?
So for fluoride, it would be 7
Okay, where do you want me to put the unpaired electron?
on the right.
Towards nitrogen. Okay. So we've double dot, double dot, double dot, single. Nitrogen has 5. So where would you suspect, or where would you like me to put the pair?
At the top.
A pair on the top. Okay, that'll work. And then what about the other 3?
The left, right.
Left, right, and bottom. Good. Let's go ahead and do that. Oxygen?
So it has 6.
6. Okay.
The single would go on the left, and then another one on the bottom, and then the other.
Pairs here and here? Okay, so we've got the appropriate dot structure for each atom. And because we know it's a molecule, we're going to start by forming single bonds between the atoms anyway. So here's a single, and here's a single. We're good? Now, are the octets satisfied? For any of them?
Just for fluoride.
Fluoride, right, fluoride's fine, it's got 8. 2, 4, 6 in a pair is 8. So it's done. It's not going to take any more sharing, it's done. What about nitrogen? It sees 7, it needs 1 more share. What about oxygen? C7 needs 1 more share. So what am I going to do?
The only unpaired ones, like,
Okay, so bring the unpaireds towards each other and share them. Are the octets full now? Yeah, we're done. Now, this is where we're going to, and I don't want you to worry about it for this exam, but this is where we're going to slowly start to kind of go towards the next module, where technically, and it wouldn't be wrong if you did it this way, but technically, as we look at oxygen, you'll notice that they've got bonds here and 2 pairs of unbonded electrons. Technically, we're going to learn next module that we would actually represent it this way and put them on the angle, because the distance from here to here, here to here, and here to here is equal. They all be 120 degrees apart. So we would show it that way. And hopefully if you see something like that on the exam, you'll just recognize it's right. It's just maybe the dots are shown a little bit off. Don't take that against the question, because sometimes people that are used to working at the next level of understanding do that when they draw it. And if you Googled it, that's probably what you found too, is on the angle. And you're like, why is it on the angle? We'll get there. Now, it would not be appropriate for you, however, to do that. They're not going to be like that. They're still going to remain a pair. Okay, so whenever you have singles, you want to bring them together to form pairs. I think that comes in play in a later question. So, any questions on drawing this structure? Oh, there we go. Based on their Lewis structures, which is the easiest to break? And who's our question answerer? Okay, Derek. Now, first of all, you have to know what the Lewis structures are, right? So let's go ahead and do these real quick. Okay, you've got carbons and hydrogens. Which one is going to be the center or center atom or atoms? The carbons, okay? So the carbons are going to be centered. Now I've got 4 hydrogens, right? So if we did carbons like that, we know we're going to bond there. Okay? Any idea where the hydrogens are going to go? For symmetry, if you sat and dealt with this for a while, if I've got 4 and I've got to divide it between 2, just like I told you before how they're going to be kind of angled, we're going to do the same thing here. It's going to end up looking like okay. So if we did this the straight way, the squared way, the squarish way, you know, it looks something like this. But as you looked at that, you would say, well, wait a minute, that's symmetry, right? But carbon only sees 1, 2, 3, 4, 5, 6, 7. It needs a share, and so does the other one. So you'd bring these 2 over here to form a double bond, and then you would say, well, wait a minute, my angle here to here to here all have to be equal. You kind of like bring them together to look like that. Okay. But for this exam, you know, if you ended up with this structure here, that's fine. Nice and symmetrically, everything 90-degree angles. All right. So that's my CH4 molecule. What about a PN? How many valence electrons are in each one of those? 5 each, right? Okay, you've got 5. They both have 5. Remember we did the nitrogen molecule, the N2 molecule? What was the bond between the two nitrogens? It's a triple bond. Good. Since phosphorus also has 5 valence electrons, what do you think the bonding is going to be between phosphorus and nitrogen? Yeah, I'll put them over here. Okay. Now, H2 molecule. They both just have one electron that they share, and there's our H2 molecule. So based upon their Lewis structures, which of these 3 molecules is going to be the most, or the easiest to break apart? Because it's just a single bond, right? Takes more energy to break up doubles and triples than it does singles. Okay? If column 5 elements form covalent molecules with triple bonds, what do column 6 elements between each other? Double bonds, because an O2 molecule is a double. So the other elements in there that would form a covalent molecule with each other would form doubles. Okay? Good. Extra practice problem number 7. Who's, okay. Molly, has anybody else not had a turn yet today? Structure for NF3. Dum, da, da, dum. I know you have, this wasn't homework, so you've got to actually figure this one out, right? Okay, so what are we going to look for first? Other than the fact that chocolate is melting in my pocket, that's not cool. I've got to get my chocolate out before it's all melty in my pocket. All right. I know tomorrow is Halloween, not today, but where are we going to start?
To find where they are on the
Okay.
So
So nitrogen is in column 5, 5A. Because nitrogen is in column 5A, it has how many valence electrons? So nitrogen is column 5A, so it has how many valence electrons? 5, so it has 3 unpaired, right? What about fluorine? We've already done this one. It's a column 7, so it has, which means it has 1 unpaired. So our hub, based on the most unbonded, or excuse me, the most unpaired electrons would be nitrogen. Also for symmetry, if you have 1 nitrogen and 3 fluorides, doesn't it make sense that nitrogen would be in the middle, just for symmetry's sake, right? So we're going to start with that. Nitrogen, I'm going to draw the pair and then 3 unpaired electrons. And I also have then fluoride, I've got 3 of them. Ballpark, where do you think they're going to go? Next to the unpaired, good. And I'm not going to draw all the dots, all the paired electrons around these. I'm going to draw the unpaired, okay? Please in your mind see that there's 6, 6, and 6 more around those. Okay? But since it's a molecule, we know they have to have at least a single bond between them. And when we complete the single bonds, are the octets satisfied? Yes, they are, so we're done. Now, technically, I'd want you on your paper to put 2, 2, and 2, 2, 2, and 2, 2, 2, and 2 around it to show me there's 6 unbonded electrons and 1 pair of bonded electrons. Okay? All right. Nitrogen nitrogen trifluoride, right? Nitrogen trifluoride. I almost said tetrafluoride, but that'd be 4. Nitrogen trifluoride. CCl2S. Who's up? Okay. CCl2S. What is going to be our pivot atom? It's going to be carbon. If you see carbon up here, it's going to be carbon. That's kind of the way it works. Okay? Because carbon's going to have 4 unpaired electrons, it's got to be a column 4 element to have more than that, or the same as that. It can't have more than that, right? So we'll put carbon And then we have 3 other pieces, right? We're going to put those around it in some way. I'm just going to go ahead and put Cl, Cl, S. Now, I'll draw all the dots on this one just so we can work through it together. Carbon, we had 4. Chlorine, 7. What about sulfur? 6. So there's 1, 2, 3, 4, 5, 6. What are we going to do next? Okay, we have to form single bonds, right? So we're going to form the single bonds because if they're not bonded at all, they're not part of the molecule. They have to be at least singly bonded together, right? Now we look at the octets. Start with the outside atoms. Are the octets satisfied? Chlorine's satisfied, but sulfur's not. What about carbon? Carbon's not. So we've got 2 atoms here that aren't satisfied, right? How many more does sulfur need? Needs 1. How many more does carbon need? We can strike a deal. We bring the unpaired electrons next to each other and bond them. We share them. Now are carbon and sulfur satisfied? Yes, they are. Okay? Now again, you're going to learn that this could be drawn like that. So they're all equidistant apart. And then also the sulfur, the electron pairs would be written like that. Okay? But again, I'm teaching you something, adding something that'll help you next module. For this module, if you don't do that, that's fine. This is the base understanding that I want you to have right here and represent it that way, if that's what makes sense to you, okay? I'm not going to give you bonus points if you do the other, so don't like force yourself to do it and make a mistake. Get it right this way, and we'll move on to the next module. If this is really simple, then go for it. Here we go. SiS2. So who's going to be the sissy? Oh, that would be, all right. All right, so let's go.
The SI is going to be in the middle
Why?
because it's got 4.
4 unpaired electrons. Also for symmetry, I've got 1 of one, 2 of the other. It makes sense that the single would be in the middle. So both satisfied. Silicon is going to be in the center. You said it has how many valence? 4, okay. So I draw 4. 2 sulfurs.
On either side. They have 6.
Just to keep it fun. There's nothing wrong with presenting it that way. Is that okay? 6, 6, 4, okay. Now don't get confused by the dot on the I in sulfur, okay? That's not an electron. It happens. Yes, it happens. Somebody here might, well, I won't say somebody will, but people often get it wrong because they count up the I, the dot on the I in silicon as an electron. So.
There's a double bond between the sulfurs and the silicon.
Well, we know there's got to at least be a single. Let's start there. So there's got to at least be a single. So just for process, let's start with that. There's the single bond between the sulfurs and the silicon. We look at it and nobody's satisfied. Everybody's looking for another dance partner, right? Because it's 2, 4, 6, 7, 2, 4, 6, 7, 2, 4, 6, 7, right? Or actually 2, 4, 6 for silicon. Silicon's looking for 2 and each sulfur's looking for 1. So it's pretty simple. We'll bring the unpaired and unpaired and unpaired and unpaired. Okay? So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 9. No. For those of you that are in advanced chemistry module 4, it's like that. Both of those would be accepted. CS gas. CS. Who's up? Stephen. All right. So which is the center? Oh, there is no center. There's only two of them. The center is the nothing between them, right? But well, let's go ahead. C and S. All right. So, sorry. Not everything is supposed to be a trick question, but there's no center between two. So, carbon is going to have how many valence? 4. All right. Sulfur? 6. Next step? Okay, I need at least one single bond, so let me go ahead and make that single bond. Is anybody happy? No.
You take the 12s and like move them and connect them.
Which one?
The 12.
The 12 o'clock positions? So I'll take both 12 o'clock positions, move them here. What about now? What's going on here?
Someone's very sad.
Wait a minute. Like, nobody's happy, are they? Well, sulfur's happy. Are they? Is carbon happy? No, carbon's not happy. Sulfur's happy, but carbon's not happy. We have a predicament, huh? What are we going to do? You keep getting the hard ones, Stephen. I don't know what's up with this. What are we going to do?
Just darn happy, I guess.
No. No, there is a Zelda here. Zelda is my name for the happy medium. Okay? So I don't say, can we find a happy medium? I say, can we find Zelda? Okay, so Zelda does exist for this molecule. Where might it be? How can carbon get 2 more and sulfur not lose any? Anybody have a guess? Carbon, how would carbon get 2 and sulfur not lose any? Go ahead.
Move the double, the 2 on the right into make it a triple bond.
Well, to make it symmetric, I'll move these 2 and make a triple bond. And then I'll take this single, and I told you to represent them as pairs. So this is the first molecule you've seen where the sharing happens by one of the atoms giving both the electrons to be shared. So sulfur shares 2 electrons with carbon, and now both octets are full. Okay. So it wouldn't be intuitive to you to sit down and figure that out, but if I told you this CS molecule is a legitimate molecule, figure it out. Start by pairing unpaired unbonded electrons. Do that first. But once you have everything paired up, you're not going to violate it by, you'd have to form a quadruple bond, okay? We're not going to go there. Look to see if you can donate 2 electrons from one atom to form the double bond, or to form the bond. Carbon couldn't do this without giving one and sulfur giving one, but then we'd need yet another one. It just isn't going to work. So you're not going to see this very often, but there is a potential for one of the atoms to donate 2 electrons, not just 1. SBr2. They're so forceful. Like an ox in a china cabinet, huh? There is a middle one, right? Because we've got more than 2, so there is a middle one. Okay, so we're going to go ahead and just assume that's going to be symmetric. But we also know that sulfur has how many? 6, and I'm going to go ahead and assume that we're going to need them here, right? And bromine has 7, so I'll put the singles inside. And we've got to have at least a single bond. Are we done? Yeah, we're done. It could be drawn that way. It could be drawn could be drawn that way. Okay. And this looks very different in 2 dimensions. When we get in 3 dimensions, it'll look exactly the same. And that's part of the rub. Okay, so in 2 dimensions, it looks like there's multiple ways to draw it. When we go to 3 dimensions, there's really only one way to draw it. But it's because of it, taking something in 3 dimensions and squishing it into 2 makes it look like there's more than one answer. Who's got the most difficult question on the page? Oh, that would be, okay. This is where I wish the smartboard was really working, because this is going to look so great on the video, but sorry, video people. All right, so looking at the problems 7 through 11, looking at all those different molecules, and there are no more questions after this, so there you go. You're just the keeper of the towels. Okay, keeper of the wipes. Which would be the hardest to break based upon their Lewis structures? For review, there was nitrogen trifluoride, there was, let's see, we had carbon, we had those are the 5 different molecules in question. Based upon their Lewis structures, which would be the hardest to break? Triple, right, but I want you to say it this way. CS. Go ahead, try. CS. No. Say it. CS. No, not CS. It's CS. Say it like you believe it, not like you're asking me a question. Is this, which, okay, here we go. Ready? Which of these molecules is the hardest to break based on their Lewis structure? The voice doesn't go up, the voice goes down. It's not CS, it's CS. Okay, because when you say CS, you're asking me a question, right? It's the way our language works. I know you can't maybe write it, but you can at least say it right, okay? Because this would be what? S-E-E-E-S? C-E-S? Okay. Siesta? So, okay, but, so it's not, what's the answer? A? No, no, no. The answer is A. Okay, so here the answer is not CS, it's CS. Correct. The answer is CS, because of the triple bond. Which would be the next most difficult to break up? SIS2? No. SIS2. Why? Double bonds, right? Which would be the next hardest, which would be like the 3rd hardest or 2nd simplest.
CCl2S.
Right, because it has a double bond in there, but it has single bonds too, right? And then SBr2 and NF3, both, all they have are single bonds. So they're like, rip those, right? So it's not like NF3? No. NF3. Any questions?
No.
No questions.
Not at all.
Okay. Doesn't have to be manly, it just has to inflect down. When you inflect up, it's a question. When you inflect down, it's a statement.